Hello, everyone. Today we're going to go over section 2.3, Other Counting Tools. So we ended the last section with using the factorial to count the number of ways to rearrange an entire collection. However, we usually do not really care about everything from a collection. For example, when dealing cards from a standard deck, many games do not deal out the entire deck. Instead, each player is dealt a hand of a few cards, and most of the deck remains untouched. Since we do not care what the contents of the rest of the deck looks like, there are in reality far fewer distinct options than what we may have counted with the factorial. In this section, we will explore two tools for selecting part of a collection. So first, we're going to talk about permutations, and these are situations where the order matters. Let's take 10 cards from a standard deck of playing cards, say the ace through 10 of spades. Shuffle these cards and deal 1. There are 10 possible outcomes. The sample space would have the ace of spades, the 2 of spades, all the way up through the 10 of spades. If we continue by dealing a second card, there are 9 possible outcomes left. Once we deal one card out, that card cannot come up again. Finally, deal out a third card, and we have 8 ways for that to happen. All told, we can use the counting principle to calculate that there are 10 times 9 times 8, or 720, different ways to deal out these cards. Notice, if we have this fraction here, which would have 10 factorial on top, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and 7 factorial on the bottom, which would be 7 times 6 times 5 times 4 times 3 times 2 times 1. The string of product from 7 to 1 being the same on the top and the bottom can cancel away, just leaving us with 10 times 9 times 8, which was the calculation we just did. So we can say 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial, would be 3,628,800 over 5,040, which also gives us the 720 that we get with 10 times 9 times 8. If we had a deck containing n cards and we dealt out r of them one by one, then there would be n minus r cards left in the deck when we were done. There are then n factorial different ways to rearrange the deck, and n minus r factorial different ways to rearrange the leftover cards. Dividing these values, n factorial over n minus r factorial gives us the number of ways to deal the r cards. So if we go back and look at this calculation that we did, and maybe go back even further and look at the situation, we had 10 cards. We were dealing 3 cards out of those 10. So 10 cards means 10 factorial on the top. Dealing 3 of those cards out means 10 minus 3 factorial on the bottom, and that gives us our calculation. Of course, this same logic will apply to situations outside of just dealing cards from a deck. Anytime you need to pick several options from a large group, you can use the same formula. Because it comes up so often, it has been given its own name, the permutation formula, or less formally, the pick function. It is usually denoted as NPR and can be found as a built-in feature on many calculators, including the suggested calculator for this course. You can get the NPR function by going to the probability button. So NPR, or n pick r, if you want to say it that way, would be n factorial over n minus r factorial, where n is the number of things we're looking at total, and R is the number of things that we are looking at dealing out of the total amount. So let's look at example 1 and step away from the deck of cards for a minute. A lottery machine contains ping pong balls numbered 1 through 25. The lottery game draws 4 numbers from this machine without replacing the ping pong ball. And a winning number matches all 4 numbers in the order that they were drawn. How many different possible lottery results are there? Since the situation says matches all 4 numbers in the order that they were drawn, that means that order matters. So this is an example of a permutation. So we can go through our 4-step problem-solving process. Step 1, understand the problem. In this problem, we have a group of 25 objects, the ping pong balls, and we pick 4 in a specific order without replacing them. Step 2, devise a plan. We are asked to select a subset of options where the order matters. This can be modeled by the pick function or the permutation. Let's carry out the plan. In this case, our NPR would be 25P4. In other words, there's 25 total options, and we're picking 4 where order matters. Plugging it into the function, that would be 25 factorial on top, 25 minus 4 factorial on the bottom. And if we simplify that, we get 25 factorial over 21 factorial. The 21 factorial would cancel out of the top and the bottom, leaving us with just 25 times 24 times 23 times 22, or 303,600. And if you used your calculator to evaluate 25P4 straight away from the probability menu, you would get 303,600 right away without doing the intermediate calculations. So looking back at our result, there are 303,600 different possible results in this lottery game. Now, permutation is where order matters. Combination is where order doesn't matter. So to win the grand prize in the last lottery game we looked at, you needed to match the 4 numbers drawn in the order that they were drawn. Let us consider a slightly easier game to win. We will still draw the lottery. Sorry about that. We will still draw the lottery in the same way, but a winning ticket only needs to match the 4 numbers. It no longer matters what order they were drawn in. So as long as you match the 4 numbers in any order, you would win. Under these relaxed rules, how many possible winning numbers are there? Last time we got all the possibilities, which was 303,600 with the permutation function, but we counted things that we don't care about now, namely the number of different ways that we could rearrange the 4 picked numbers. These would be repeats. Since the order doesn't matter anymore, we can divide out 4 factorial, or 24, and get a smaller number. Looking at the calculation, that would be 25 pick 4 on the top, dividing out our repeats, 4 factorial, the number of different ways we can rearrange the 4 picked numbers, which would give us 25 factorial over 25 minus 4 factorial, but now there's this other 4 factorial in the bottom, and that gives us 12,650. We've taken the repeats out. We can use this form of the formula for something called the combination. So once again, this is a useful enough formula that it's given its own name. Instead of NPR for permutation, we call it NCR for combination, or informally, we can call it the choose function. So NCR or N choose R or N combination R would be N factorial over R factorial times N minus R factorial. And again, there is a button on the calculator under the probability menu that will do this for you. But if you don't have that calculator with the special option, or if you just want to do all of the intermediate calculations, that's fine. The formula will get you the right answer. So let's take a look at example 2. To reduce costs, the restaurant asks a banquet organizer to select only 4 of the 27 items on the restaurant's menu for the banquet guests to choose from. How many different possible menus could the organizers design? So here order doesn't matter because we're choosing 4 items from the 27 items on the menu, but it doesn't matter what order these 4 items are put in. So this would be a combination instead of a permutation. So again, step 1, understand the problem. We have a set of 27 elements, the restaurant menu, and we're asked to select 4 of them. And it would appear that the order of the selection will not matter. Step 2, devise a plan. This situation can easily be modeled by the choose function. So we use a calculator to evaluate 27 combination 4, or 27 choose 4, or 27 C4, however you want to say that. The NCR formula is N factorial over R factorial times N minus R factorial. N here is 27. R here is 4. So 27 factorial over 4 factorial times 27 minus 4 factorial, which would be 27 factorial over 4 factorial times 23 factorial. 27 factorial can be written out as 27 times 26 times 25 times 24 times 23 times 22, all the way down to times 2 times 1. But since we know that we have a 23 factorial on the bottom, we can leave it 23 factorial on the top and not list out anymore, because that 23 factorial is going to cancel away. 4 factorial we can calculate as 24. So the bottom has 24 times 23 factorial. The 24 on the top cancels out with the 24 on the bottom. As we said, the 23 factorial on top will cancel out with the 23 factorial on the bottom. And this leaves us with 27 times 26 times 25, which is 17,550. If you use the calculator to do 27 choose 4 directly, you'll get your 17,550 directly without any of the intermediate calculations. So looking back at our result, there are 17,550 possible menus for the banquet, where there were 27 items to choose from, and you're picking 4 of them. Order does not matter in the 4 that you're picking. Let's take a look at example 3. In one particular card game, each player is dealt a hand of 6 cards from a standard deck of playing cards. How many possible 6-card hands are there? Understand the problem. We're taking 6 cards from a standard deck of 52. We will assume that the order of a hand of cards does not matter, because in games that use a hand of cards, the player is typically free to rearrange the cards as they desire. Order doesn't matter. We are asked to count the number of possible ways to do this. So when we devise a plan, we know it's going to be one of our functions where we're picking or choosing. And since order doesn't matter, this would be modeled by the choose function, by a combination, not a permutation. So in step 3, we carry out the plan. We can use a calculator to evaluate 52, choose 6, or we can do the entire calculation by hand. NCR is n factorial over r factorial times n minus r factorial. N is 52, r is 6. So plugging in those values, we have 52 factorial over 6 factorial times 52 minus 6 factorial. Simplifying a bit, 52 minus 6 is 46. So we have 52 factorial over 6 factorial times 46 factorial on the bottom. Writing out 52 factorial as far as we need to go would be 52 times 51 times 50 times 49 times 48 times 47. And we could leave the rest as 46 factorial so that it cancels with the 46 factorial on the bottom. We could also calculate 6 factorial to be 720. So the 46 factorial on the top cancels with the 46 factorial on the bottom. That just leaves us with, on the top, 52 times 51 times 50 times 49 times 48 times 47. On the bottom, we just have 720. Now you're going to want to use a calculator for this piece. The 52 times 51 all the way to times 47 gives us 14,658,134,400 divided by 720, which is 20,358,520. And again, if you used a calculator and the combination function directly and put in 52C6, you would get your 20,358,520 directly without having to do the intermediate calculation. So looking back at our result, there are 20,358,520 possible different hands that could be dealt in this game. So now let's look at solving combinatorics problems. These are problems involving combinations or permutations. Combinations, order doesn't matter. Permutation, order matters. So as is often the case in problem solving, the toughest part of the process is deciding which method suits the situation. We now have 5 different tools available for counting the number of possible outcomes to an experiment. If the experiment is simple enough, we can simply list every possible outcome and count them. If the situation combines several independent experiments, we can use the counting principle and multiply the count for each simple experiment together. If the experiment involves rearranging an entire set of objects, we can use the factorial. And before today, those were the only 3 methods that we knew. But now we're adding in, if the experiment involves selecting a subset of a group where the order matters, we could use the pick function or a permutation. If the experiment involves selecting a subset of a group where the order does not matter, we can use the choose function or a combination. To further complicate matters, there is usually more than one correct way to set up a combinatorics problem. If you try a different approach than the one presented here but get the same result, then your method is almost certainly also valid. Example 4. In the Kentucky Derby, 20 horses race on a 1.25-mile track. The superfecta bet is an attempt to predict the first, second, third, and 4th place finishers. How many different options are there for a superfecta bet? Well, let's understand the problem. In this situation, we have a set of 20 elements and are asked to select 4 of them in order Here, the order matters. You're predicting the first place, the second place, the third place, and the fourth place. You're not just picking 4 horses and hoping that they come in one of these 4 places. The prediction is for the first, second, third, and fourth. Order matters. So let's devise a plan. Since the order matters, we can model this situation using the pick function, or a permutation. So, carrying out the plan, we calculate 20p4 because there were 20 to choose from, and we are picking 4 out of those 20 where order matters. So NPR is n factorial over n minus r factorial. That would be 20 factorial over 20 minus 4 factorial, or 20 factorial over 16 factorial, since 20 minus 4 is 16. Listing this out, 20 factorial as far as we need to take it would be 20 times 19 times 18 times 17 times 16 factorial. We can stop there because we have a 16 factorial on the bottom that's going to cancel away in our next step. That just leaves us with 20 times 19 times 18 times 17, which is 116,280. Or if you use the calculator's permutation function to do 20p4 directly, you would get the 116,280 without having to do the intermediate calculation. Looking back at our result, there are 116,280 different possible superfecta bets at the Kentucky Derby. So not an easy win. Example 5. In one particular board game, success is determined by rolling a 20-sided die and an 8-sided die. How many different possible results are there for this roll of the dice? So let's understand the problem. There are 2 unrelated things happening in this situation: rolling a 20-sided die and rolling an 8-sided die. Since we have 2 unrelated events, we can use the counting principle to determine the number of ways these 2 experiments can be combined. There's 20 possible ways to roll the 20-sided die. There's 8 possible ways to roll the 8-sided die. So we multiply 20 times 8, and we get 160. So there are 160 different possible results for rolling these dice. So this one wasn't a permutation. It wasn't a combination. It was a situation where we use our methods from last time, namely the counting principle. Example 6. 12 people were invited to a banquet. How many different options does the host have for arranging his 12 guests around the table? So understand the problem. For this situation, we are interested in the number of different ways to rearrange 12 things, the guests at the banquet. We're rearranging all 12 of them and using every element. That means that this one is a factorial problem. So we use the factorial to model the situation. Carrying out the plan, we can use a calculator and do 12 factorial, or use a calculator and actually multiply out what 12 factorial is if we don't have the factorial button. But we would have 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We get 479,001,600. So looking back at our result, there are 479,001,600 different possible seating arrangements for this banquet. Again, this wasn't a combination or a permutation, this was a factorial because we are rearranging all of the elements. Example 7. A class of 18 students needs to be divided into 3 groups of 6 students each. How many ways could the teacher form these? It says 4 groups, apologies. It should be 3 groups. How many ways could the teacher form these 3 groups? Step 1, understand the problem. Take a set of 18 elements, the students, and form 3 groups of 6. The order that elements are assigned to the groups does not appear to matter. So if you're a group of 6 students, it's not like each student is assigned a different task. It's just a group of 6 students that's like a hand of 6 cards. The order does not matter. So let's devise a plan. To solve this problem, we need to look at each group separately. We can use the choose function to form one group of 6 from our choice of 18 students. That leaves 12 students left, and we can use the choose function again to form the second group of 6. Finally, there will be 6 students left to form the third group. Once we know the number of ways to form each group, we can then use the counting principle to find the total number of ways to split the class. So let's carry out this plan. For the first group, we find 18 choose 6. So we use our NCR function, n factorial over r factorial times n minus r factorial. N is 18, r is 6. So we plug those in. We get 18 factorial over 6 factorial times 18 minus 6 factorial. 18 minus 6 is 12. So we have 18 factorial over 6 factorial times 12 factorial on the bottom. Writing out 18 factorial as far as we need to go would be 18 times 17 times 16 times 15 times 14 times 13 times 12 factorial. We can stop there because there's a 12 factorial we can cancel with on the bottom. And 6 factorial calculates as 720. Canceling out the 12 factorial, that leaves us with 18 times 17 times 16 times 15 times 14 times 13 on the top, 720 on the bottom. Use a calculator to multiply this out. That's 13,366,080 on top, 720 on the bottom. That's 18,564. So in the first step of carrying out our plan, 18 choose 6, 18 combination 6, or 18C6, however you want to say that. You can put that directly into your calculator's choose function and get the 18,564 directly that way without having to do any of the intermediate calculation. We're not done though. This was just for the first group. There were 18 students. We chose 6 to make the first group. That leaves us with 12 to make the second group. So now we have to find 12 choose 6. Plugging into our function, that's 12 factorial over 6 factorial times 12 minus 6 factorial. And apologies, that factorial right here should be on the outside of the parentheses. 12 minus 6 is 6. So we have 12 factorial over 6 factorial times 6 factorial. That gives us, writing out 12 factorial as far as we want to take it, 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial. We can leave that at 6 factorial, so we cancel with the 6 factorial on the bottom. And the other 6 factorial calculates as 720. Once the 6 factorials cancel, we have 12 times 11 times 10 times 9 times 8 times 7 on top, 720 on the bottom. That would be 665,280 on top, 720 on the bottom. And dividing, we get 924. If you want to skip all that intermediate calculation, you can use the choose function in your calculator. 12 choose 6 will give you 924 directly. We're still not done because that was the second group only. We have to now account for the third group. But for the third group, there's only one option. We have 6 students left. We need a group of 6. The only one option is that we pick every student remaining. So when we multiply together the choices for the first group times the choices for the second group times the choices for the third group, that's 18,564 times 924 times 1, which is 17,153,136. So looking back at our result, there are 17,153,136 different ways for the teacher to divide the class into 3 groups. Now that we have more tools for counting, let's go back and consider probability and expected value one more time. Example 8. In a fictional state lottery game, 48 balls numbered 1 through 48 are placed in a machine, and 6 of them are drawn at random. If the 6 numbers drawn match the numbers that a player had chosen, the player wins the grand prize of $1 million. If they match only 5 numbers, they win the second prize of $1,000. It costs $1 to buy a ticket. What is the expected return on one ticket? So let's understand the problem, break down the situation. We're drawing 6 numbers from a set of 48 in any order. For the grand prize, we match all 6 numbers, we win $1 million. For the second prize, we match any 5 of 6, we win $1,000. One ticket costs $1. We're asked to find the expected value of a lottery ticket. Let's devise a plan. Solving this problem will need several steps. We're asked to find the expected value of a lottery ticket. To do that, we need to know the probability of each possible result. To find that, we need the number of ways everything can occur. So we'll start by looking at the number of ways that numbers can be drawn from a pot, the number of ways to win the grand prize, and the number of ways to win the second prize. Next, we can look at all of the possible events, their probabilities, and their return value. Using that, we can finally calculate the expected value of this lottery game. So this is the most complicated example we have had in this unit. So let's carry out the plan. In this game, we draw 6 balls from a pot of 48 balls. The order that the balls are drawn does not matter. We only care if the number appears on our lottery ticket or not. Thus, it's a combination, and there are 48 choose 6 possible different lottery drawings. So we have our combination function, n factorial over, on the bottom, r factorial times n minus r factorial. N is 48, r is 6, so we plug those values in. We have 48 factorial on the top, and 6 factorial times 48 minus 6 factorial on the bottom. 48 minus 6 is 42. So 48 factorial on the top, 6 factorial times 42 factorial on the bottom. Writing out our 48 factorial as far as we need to take it would be 48 times 47 times 46 times 45 times 44 times 43 times 42 factorial. And we can leave that at 42 factorial because we want to cancel with the 42 factorial on the bottom. 6 factorial calculates as 720. So the 42 factorials cancel, and we have 48 times 47 times 46 times 45 times 44 times 43 on top, 720 on the bottom. That's 8,835,488,640 on top, 720 on the bottom. When we divide, we get 12,271,512. So we found that 48C6 is 12,271,512. And again, you can use that choose function in your calculator and get it straight away without having to do all that intermediate calculation. There is one winning event. So the probability of winning the grand prize is 1 in 12,271,512. To win second prize, your ticket must have exactly 5 of the 6 numbers drawn from the pot, and the 6th number on your ticket must be one of the 48 minus 6 or 42 numbers not drawn. So this would be 6 choose 5, 6 winning numbers, and you have to have any 5 of them. So the order doesn't matter. It's a combination, and it would be 6 choose 5. That's for the first 5 numbers. And then for the 6th number on your ticket, because it can't be one of the winning numbers, otherwise you would have a grand prize ticket, there are 42 numbers that weren't drawn. You need one of those 42 for your 6th number. We can multiply these two combinations together using the counting principle and get the number of possible second prize winners. So first, we'll use NCR to calculate 6C5. That's 6 factorial over 5 factorial times 6 minus 5 factorial. That's 6 factorial over 5 factorial times 1 factorial. And since 1 factorial is just 1, 5 factorial times 1 is 5 factorial. We can write out 6 factorial as far as we need, and that's just 6 times 5 factorial, because the 5 factorial is going to cancel, and that just leaves us with 6. So 6 choose 5 is just 6. Next, we'll calculate 42 choose 1. So n is 42, r is 1. That's 42 factorial over 1 factorial times 42 minus 1 factorial. That's going to be 42 factorial over 41 factorial. We can write out 42 factorial as 42 times 41 factorial. The 41 factorials cancel, leaving us with just 42. So 6 choose 5 times 42 choose 1 is 6 times 42. So there are 252 ways to win second prize. Out of the 12 million sum that we found for how many different possible combinations there are. So the probability of winning the second prize is 252 over 12,271,512. Now we put this information into our table for expected value. For the grand prize, the outcome is not 1 million because you have to subtract the $1 that you spent. The grand prize would be considered 999,999 times the probability of 1 over 12,271,512 gives us this row's value, outcome times probability, of 0.081489. For the second prize, you don't win $1,000. You have to subtract the $1 you spent, so you win $999. Times the probability of getting the second prize that we found of 252 over 12,271,512. The outcome times probability for this row would be 0.020515. And finally, the option where you lose, the outcome there would be negative $1. You lose the entire dollar that you spent. The probability here, well, out of the 12,271,512 outcomes, 1 wins the grand prize and 252 win the second prize. That leaves subtracting 253 outcomes from the total number of outcomes, 12,271,259 losing outcomes. So the probability of losing is 12,271,259 out of 12,271,512. Multiplying our negative $1 times that probability, we get negative 0.999979. Adding up this column, we get an expected value of negative 0.897975. So on average, looking back at this result, you can expect to lose about 89.8 cents on each lottery ticket. And that tracks, because remember, we're expecting to lose most of what we spend when we have a lottery or casino game. Players, beware. Of course, in the lottery example, no one will ever actually lose 89.8 cents playing the lottery. Most players will lose exactly $1, while a relative lucky few will win a sizable return. Remember, expected value is what your average will be if you play the game enough times. In general, if the expected value of a game is negative, it is not a good idea to play the game, since on average you will lose money. It would be better to play a game with a positive expected value. Good luck trying to find one. Although keep in mind that even if the average winnings are positive, it could be the case that most people lose money and one very fortunate individual wins a great deal of money. If the expected value of a game is 0, we call it a fair game, since neither side has an advantage. Not surprisingly, the expected value for casino games is negative for the player, which is positive for the casino. It must be positive or they would go out of business. Players just need to keep in mind that when they play a game repeatedly, their expected value is negative. That's fine so long as you enjoy playing the game and think it's worth the cost. But it would be wrong to expect to come out ahead. That's section 2.3. Next time I see you, we're going to go ahead and go over the homework from section 2.3.